Welcome to Math TV with Professor V. In this video, we're going to look at specific examples of evaluating improper integrals. If you haven't already watched the introductory video lecture on improper integrals, I'll link it here. Make sure you watch that first because that's where I lay all the foundation. And in this video, we're just going to crank through some examples and have a good old integration party. So here we go. First improper integral we're going to look at is from 6 to infinity dx over x squared minus 25. And when you're evaluating an improper integral, you basically just need to determine whether or not it converges or diverges. And if it converges, we'll specifically say what it converges to. Okay. So let's see what is making this integral improper. It's probably pretty clear. We notice the upper limit is infinity. I also notice that the function, the integrand, is not defined at plus or minus 5, but I'm not worried about that because the limits of integration are from 6 to infinity. So it doesn't include those values, so I don't have to worry about rewriting my integral to account for that. Okay, so now first thing before you even think about figuring out how to integrate this sucker is you rewrite it as the limit as t approaches infinity from 6 to t of dx over x squared minus 25. Okay, so now we can see the function that we're integrating is 1 over x squared minus 25. That is a perfect circumstance to use our partial fraction decomposition because we're integrating a rational function. So x squared minus 25, that's a difference of squares. I'm going to factor it into x minus 5 times x plus 5. And so the decomposition will have the form a over x plus 5 plus b over x minus 5. If you need a review of how to do partial fraction decomposition, I'll link it right here. Upper right, just click away. And then we're going to multiply through by the LCD, which is x plus 5 and x minus 5. So we're trying to solve for a and b. And then here we're going to end up with 1 equals a times x plus 5. Oh no, x minus 5. X plus 5 is going to cancel. Plus b times x plus 5. Okay, and then we can go ahead, let's let x equal 5. If I plug in 5 for x, I'm going to have 1 equals a times 5 minus 5 plus b times 5 plus 5. This term's just going to go to 0. So I'm left with 1 is equal to 10b. So b is 1/10. Very nice. And then in order to solve for a, we can just go ahead and let x equal negative 5. Remember, you try to zero out those factors. So if x is equal to negative 5, then we have 1 equals a times negative 5 minus 5 plus b times negative 5 plus 5. And then from here, we've got 1 equals negative 5 minus 5. That's going to give me negative 10 times a. This is just 0. So now we know that a is equal to negative 1/10. All right, cool. So that means our partial fraction decomposition has the form negative 1/10 over x plus 5 plus 1/10 over x minus 5. If you'll notice back to where we had a and b set up. What we could do, since I know we're going to integrate it in a second, I'll just factor out 1/10 and then I could write it as 1 over x minus 5 minus 1 over x plus 5. Doesn't that look better? I like it a lot better. Okay, so now that we've gotten that handled, we can go back to the original problem. So we have, make sure you write lim on every single step until you finish evaluating the limit. So limit as t approaches infinity. Remember, our limits were from 6 to t. And then now I have 1/10 times 1 over x minus 5 minus 1 over x plus 5 dx. Very good. Okay, so let's go ahead. We can anti-differentiate this, no problem. We have the limit as t approaches infinity. This 1/10, I'm just going to bring it down. It's just a constant, so it comes along for the ride. And then antiderivative of 1 over x minus 5, that's going to be natural log absolute value x minus 5 minus, and then similarly, antiderivative of 1 over x plus 5 is going to be natural log absolute value x plus 5. And this is all getting evaluated from 6 to t. Very good. Okay, let's see here what we've got going on. I can use my log properties to combine these into a single logarithm. So let's go ahead and do that. We've got the limit as t approaches infinity of 1/10 ln absolute value x minus 5 over x plus 5. And this is evaluated from 6 to t. And then we can go ahead, substitute in our limits of integration for x, okay? All the while writing lim as t approaches infinity every step of the way like little calculus angels. So limit t goes to infinity 1/10. We've got ln absolute value t minus 5 over t plus 5 minus ln absolute value 6 minus 5 over 6 plus 5. Okay, good. Now we need to take the limit. So notice here I have ln of absolute value t minus 5 over t plus 5. So if you want to work on this separately just for a second, we've got the limit as t approaches infinity. I'm going to ignore the 1/10 for now. So we have ln absolute value t minus 5 over t plus 5. I can pass the limit inside the natural log. So we've got natural log absolute value limit t goes to infinity of t minus 5 over t plus 5. Okay? Numerator is approaching infinity, denominator is approaching infinity. In this case, you can multiply numerator and denominator by 1 over t if you want. Okay, so then you would have ln absolute value limit t goes to infinity. This would be 1 minus 5 over t over 1 plus 5 over t. And then as t goes to infinity, 5 over t, that'll go to 0. That'll go to 0. And you're just left with 1. So then we have natural log of 1, which is just 0. Okay, that's the super precise way to do it. You may have noticed degree of the numerator is 1. So is the degree of the denominator. So when you're finding the limit as t goes to infinity, you can just divide the leading coefficients. 1 divided by 1 also gives us 1. That's more the pre-calc or shortcut way of doing it. So just check with your instructor, okay, before you take little shortcuts. So we know this whole term here, ln t minus 5 over t plus 5, back to this big limit here. I know this is going to be approaching ln of 1. That's where that's going. Okay. So let's copy this and then keep working down here. All right. And then this is just going to be a constant, this second term right here. This is just some constant. And ln of 1, that's equal to 0. So now we can put everything together. I don't have to write lim as t goes to infinity because I've taken the limit. So we just have 1/10 times 0 minus ln. I'm going to have 1 over 11 left over. Yes? Cool. So this is negative 1/10 ln 1 over 11. And then hopefully you remember some properties of logarithms. Remember that coefficient, just the -1. I'm not moving the 1/10. I'm just going to move the negative back to the argument here and make it the exponent on 1 over 11, which means take the reciprocal. And so our final cleaned up snazzy answer is 1/10 natural log of 11. Okay. Good. Since this is finite, right? This is finite, then we know that the integral converges. Good. We would say the integral diverges if the limit ended up being infinity, negative infinity, or does not exist. Any one of those. How are you doing? Did you like that one? Okay. Got a couple more. Let's look at example number 2. We've got the integral from 0 to infinity, 36 times 1 plus tan inverse of x over 1 plus x squared dx. Okay, so first things first, before you even think about integrating, you're going to rewrite using a limit. So we have the limit as t approaches infinity, 0 to t, 36 times 1 plus tan inverse of x over 1 plus x squared dx. All right, so now let's think how to integrate this. First thing that pops out to me is that we have this 1 plus x squared sitting in the denominator. And I know 1 over 1 plus x squared is the derivative of tan inverse of x. So I'm inclined to use a u substitution. And I'm actually going to throw the 1 in there because why not? So let's see if that will work. Let's go ahead and say we're going to let u equal 1 plus tan inverse of x, all right? And then what would du be? So derivative of 1, that's a constant, that's just going to be 0. And then derivative of tan inverse of x is 1 over 1 plus x squared dx. Perfect, right? That's exactly what we have here. And then let's rewrite everything. So we've got the limit as t approaches infinity. Now you guys, we have to change our limits of integration, okay? Currently they're in terms of x. I need to change them so that they're in terms of u. So go back to this statement here and plug in the limits that we have for x. So u of 0 would be 1 plus tan inverse of 0. Tan inverse of 0 is 0, so this is just 1. And then the upper limit would just be 1 plus tan inverse of t. Okay, so these are our new limits of integration. Change them as soon as, oh, that should be a t, sorry. Change them as soon as you do the u substitution. Everything should match. So now we have here 36u du. So once my integral, right, is in terms of u, the limits better match. Change them pronto. I told my class the other day, change it right away like you would change a dirty diaper on a baby, right? You don't just let it fester. Gross. Okay, so change those limits. Good. Can we integrate 36u? I certainly hope so. Easy breezy, just add 1, divide by the new exponent. So we've got limit t approaches infinity. It's going to be u squared over 2, but since we have that 36 sitting out there, now it's just 18u squared. And this gets evaluated from 1 to 1 plus tan inverse of t. Okay, very nice, very nice. Now we have limit t goes to infinity. Keep the 18 outside, please. And then I'm going to substitute in my limits of integration for u. So we'll have 1 plus tan inverse of t squared minus 1 squared, like so. Okay, so now as t approaches infinity, most of the terms here are just constants, right? 18 is a constant, 1 is a constant, this is a constant. So really all I need to do is figure out what is the limit as t approaches infinity of tan inverse of t. And you guys, it just comes down to, did you bother learning what the graph of tan inverse of x looks like when you were in trig or pre-calc? Maybe, maybe not. If you forgot, I'll remind you. That was supposed to be nice and straight. Come on, cooperate. Here we go. Tan inverse. Do you remember what the graph of regular tangent looks like? Maybe, maybe not. Regular tangent, original flavor, like this. Asymptotes at pi over 2, negative pi over 2, goes through 0, 0, kind of looks like x cubed, okay? This is regular y equals tangent of x. That's just one period. It keeps repeating every pi. Tan inverse, remember when you find an inverse function, you interchange x and y. So just think to yourself, those vertical asymptotes become horizontal asymptotes. They're at pi over 2 and negative pi over 2. 0, 0 stays 0, 0, and it just looks like it got knocked over on its side. Okay, so here's remix y equals tan inverse of x. Okay, so this is what you need to have in your mind so you can take this limit. The limit as t approaches infinity, positive infinity, of tan inverse of t is equal to? Why, yes, it's pi over 2. And if instead we had approached negative infinity, what would that limit be? That would mean we're going this way. So that limit would be negative pi over 2. Not that we need it for this problem. I just want you thinking because tan inverse of x comes up a lot in calc. So you need to know the derivative of it, how to take limits with it, all that good stuff. Okay, so this is going to pi over 2. Let's copy this and continue below. That was the briefest little trig review, but that got the job done, hopefully. So we've got now limit. Oh, no more limit. We took the limit. So I've got 18 times 1 plus pi over 2 squared minus 1. See how there's no more t, so I'm not writing lim as t goes to infinity anymore. We took it, the limit. We're good. 18 times, let's multiply this out. So this is going to be 1 plus 2 times 1 times pi over 2 is just pi, plus pi squared over 4 minus 1. And then check this out. The 1's cancel. And all I'm left with is 18 times pi plus pi squared over 4. You could leave it like that, or if you feel like taking a pi out, maybe 18 pi times 1 plus pi over 4. Maybe that looks moderately better. Either way, we're done. All I care is that this is finite, therefore that means the integral converges. Or it is convergent, okay? Ugly little number, but doesn't matter. It's finite. Okay, very good. Let's look at something a little more tricky, perhaps. Third example here. We've got the integral from negative infinity to infinity of 22x times e to the negative x dx. Oh man, look what's going on. We've got the lower limit of negative infinity and an upper limit of positive infinity. We have to rewrite this using two limits, okay? And so the way to do it is you want to split up the integral somewhere between negative infinity and infinity. You can split it up anywhere you want, okay? You can pick any number. Usually we pick 0, as long as it's within the domain here. So that's what we're going to do. So I'm going to rewrite this as integral from negative infinity to 0, 22x e to the negative x dx, plus integral from 0 to infinity of 22x e to the negative x dx. And then we need two different dummy variables for the limit. So I'll say the limit as t goes to negative infinity for the integral from t to 0 of 22x e to the negative x dx. And then pick a different variable, let's say the limit as s approaches positive infinity for 0 to s of 22x e to the negative x dx. So we actually have two integrals to evaluate here, okay? And we're going to have to take those limits. You have to do them separately. In order for the original integral to be convergent, both integrals 1 and 2 must be convergent, okay? If one of them diverges, it's game over. You know the original diverges. It doesn't matter if one goes to positive infinity and the other one goes to negative infinity. They don't cancel out. Infinity doesn't work that way, okay? So let's just pick one to get started with. Let's do, how about integral 2, just because s is going to positive infinity and it looks easier, okay? So let's do integral number 2. And I'm noticing we're going to need to do it by parts, right? Because we've got an exponential function and a polynomial. So let's set up for integration by parts. And I'm going to let u equal 22x, and dv is going to be e to the negative x dx. Good. So what would du be? Take the derivative of 22x. That'll be 22 dx. And then v is going to be negative e to the negative x. Okay, so now we've got limit s goes to positive infinity. uv, so that's going to be negative 22x e to the negative x. That's going to get evaluated from 0 to s, minus the integral of v du. But since v has a negative sign here, then this is going to make this addition, 0 to s, 22 e to the negative x dx. All right, and then this integral should be no big deal. 22 is just a constant. Antiderivative of e to the negative x would be negative e to the negative x. So I'm going to rewrite everything in the next line. We've got limit s approaches positive infinity, negative 22x e to the negative x, minus 22 e to the negative x. And then now this is all going to get evaluated. I don't like those parentheses. Let's make them brackets. So I could just put 0 to s like that. Okay? Very good. So here we have limit s approaches infinity. I'm very tempted to just take the negative 22 out really quickly. And then we have x e to the negative x plus e to the negative x from 0 to s. It'll make things a smidge easier in just a second. So now we have limit s goes to positive infinity, negative 22 times s times e to the negative s plus e to the negative s minus lower limit is going to be 0 times e to the 0 plus e to the 0. All right, very good. Now let's see what's going on here. So we've got the limit as s approaches infinity, negative 22 times, this is going to be a little tricky. So I'm going to factor out e to the negative s from both of these terms here. And then I'm going to be left with s plus 1. We'll talk about that in just a second. This is just 0, and then e to the 0 is 1. So I have minus 1 left over. Okay. Now, s is approaching infinity. All right. So let's see what's going on. This is the limit. S approaches infinity of negative 22 times. I have s plus 1 over e to the s minus 1. So if s goes to infinity, notice s plus 1 is going to infinity, so is e to the s. So in that case, we have indeterminate form of the type infinity over infinity, and we can go ahead and use L'Hopital's rule for that limit. So off to the side, we could look at the limit as s approaches infinity of s plus 1 over e to the s. Using L'Hopital's rule, now we have the limit, s approaches infinity. Derivative of the numerator, derivative of s plus 1 is going to be 1. And then derivative of the denominator, derivative of e to the s is just e to the s. And then now as s approaches infinity, I have 1 over the denominator going to infinity, so that's going to approach 0. All right, good. So that means this whole term goes to 0. I have 0 minus 1, so that's negative 22 times negative 1, so this is 22. That means this integral, integral number 2, is convergent. Does that mean that integral number 1 is convergent? No, not necessarily. So, we have to evaluate integral number 1. And remember, integral number 1 was the limit as t approaches negative infinity, integral from t to 0, 22x e to the negative x dx. Now you don't have to do all the work from scratch because remember we already integrated 22x e to the negative x. We did it by parts. So what we can go ahead and do is just copy this antiderivative right here. Or let me just copy this one right here. I'm just not going to use the same limits. We're going to change them to match the limits for integral number 1. Okay, so these are different. We're switching them. It's the same antiderivative. I just have the limit as t goes to negative infinity, and the limits are from t to 0. You see that? Okay, good. Let's take out the negative 22. I really liked how we did that last time. It was making things more clear. So let's take out negative 22, and then we're going to have x e to the negative x plus e to the negative x, and this is going to be evaluated from t to 0. Okay, so we've got limit t approaches negative infinity. This is negative 22 times, I'm plugging in 0 for x, so that's going to be 0 plus e to the 0 minus t e to the negative t plus e to the negative t. Okay, cool. So this is the limit t approaches negative infinity, negative 22 times 0 plus e to the 0 is just 1, minus, and then let's again factor out that e to the negative t, and then I'm left with t plus 1. Okay. I can rewrite e to the negative t in the denominator. So this is the limit t approaches negative infinity of negative 22 times. You know, I don't even need to. Watch this. We're pretty much done. So if t is going to negative infinity, negative t is approaching positive infinity, and e raised to the infinity, we all know what the graph of e to the x looks like, right? It's like this. So this term, this whole term right here is approaching infinity. And then t is going to negative infinity plus 1, that's going to negative infinity. So we basically have infinity times negative infinity, that's going to negative infinity. And then you've got another negative in the front, so that's going to positive infinity. But then you have a negative 22, so now it's going back to negative infinity. Either way, who cares? It's not a constant, right? So integral number 1 diverges. And what does that mean for us? That the original, the OG integral, where was it? From negative infinity to infinity, 22x e to the negative x dx is divergent. Now we were kind of unlucky. If we had decided to just evaluate integral 1 first and gotten that it was divergent, then we could just finish the problem and not even waste our time doing integral number 2, okay? But just so you know, when you're working examples, both of those integrals must be convergent for the original problem to be convergent. Okay, good. I've got one more for you, which is a little tricky because maybe you wouldn't even notice right away that it's an improper integral, you know? That can be nerve-wracking. So example 4, we've got the integral from 9 to 18 over rad 3 of dt over t times rad t squared minus 81. And you might be thinking to yourself, I don't see any infinities for the limits of integration. I don't see anything weird. Like, why is this improper? Well, notice we have a domain restriction. If t is equal to 9, then the denominator would be 0. So that would make the function undefined, and that qualifies as an improper integral. So I want to rewrite using a limit and get rid of the 9. What to do? Well, you have to decide which side you're approaching from. So look at it this way. The limits of integration are from 9 to 18 over rad 3. So I'm going to replace 9 with a dummy variable. I can't use t because that's the variable for the integrand. So I'm just going to write it as the limit as, let's say, a approaches 9. And we're approaching 9 from the right. Okay, if it's the lower bound, you're always going to be approaching from the right. If it's the upper bound, you're going to be approaching from the left. So this is a to 18 over rad 3 dt over t times rad t squared minus 81. Okay, cool. Now from here, what would you do to integrate? It's trig sub time, people, isn't it? Look, we've got this rad t squared minus 81. A u sub wouldn't help us because that t is in the denominator, not the numerator. So we're stuck unless we use trig sub. So if you have variable squared minus a constant, you use secant, yes? So we're going to let t equal 9 secant theta. And then dt would be 9 secant theta tan theta d theta. Now it's up to you. It might be a little bit messy to change the limits of integration. So you can say this, I'm fine with this if you're in my class. You can say, let's just consider the indefinite integral, not improper, indefinite integral, just so we can anti-differentiate and not be bothered with the limits for now. Okay, so we're just going to consider this indefinite integral. Let's do the trig sub, and then we'll plop everything back into the original problem with the limits. Okay, so I'm replacing dt with 9 secant theta tan theta d theta. And then t is 9 secant theta. And then I have rad t squared minus 1, so that's going to be 81 secant squared theta minus 81. Okay, looks nice. Look at this 9 secant theta canceling out like a dream. I love it so much. And then here I can take out this 81, right? And we have secant squared theta minus 1 underneath the radical. So now we've got integral tan theta d theta over rad 81. What's secant squared theta minus 1, guys? Why, yes, it's tan squared theta. Cool. I can take the square root of the denominator. That's just going to be 9 tan theta. So let's move that 9 outside. We've got 1/9 tan theta d theta over tan theta. Woo! Tan theta is just gone. Oh my goodness. And we have 1/9 integral d theta. Well, there's a 1 if you want to think of it that way. What's the antiderivative going to be? Just theta, right? So we've got 1/9 theta plus c. Because remember, we wrote an indefinite integral. And our original variable was t. So t equals 9 secant theta. I need to rewrite everything in terms of the original variable t. That means t over 9 is equal to secant theta. It's triangle time. Yes, yes, yes. So secant is the ratio of the hypotenuse over the adjacent side. And the missing, oh, we don't even need to do that. We can just say, get rid of this. We can just say, since t equals 9 secant theta, t over 9 is equal to secant theta. And that means theta equals secant inverse of t over 9. Okay? Good. So then I can rewrite my final answer as 1/9 secant inverse t over 9 plus c. Now, let's put this back in to the original that we had. Where did it go? Right here. So let's copy the original integral down below, and let's add a little narrative. So now we have, check this out, the limit as a approaches 9 from the right. I have the antiderivative. It's 1/9 secant inverse t over 9 evaluated from a to 18 over rad 3. Ooh, okay. So then we have limit, a approaches 9 from the right, 1/9. This is going to be secant inverse of 18 over rad 3 over 9 minus secant inverse a over 9. Okay, so we've got limit, a approaches 9 from the right, 1/9 secant inverse of 18 over rad 3 over 9, that's 2 over rad 3, minus secant inverse of a over 9. Okay, this is not so bad. Secant inverse of 2 over rad 3 is the same as finding cosine inverse of rad 3 over 2. So when is cosine equal to rad 3 over 2? Do you know? Yes, very good, at pi over 6. Okay, and we've got that 1/9 in the front, minus, and then we have secant inverse of a over 9, and a is approaching 9 from the right. So we've got 9 over 9, that's basically approaching 1, so secant inverse of 1. So you could think of it the same thing as when is cosine equal to 1? That's at 0. 0 radians, cosine equals 1. Boop. And so we're left with pi over 54, which is finite. So therefore we could say that the integral is convergent, or it converges, whatever. Okay, so that concludes the video. Hope you found it helpful. These are pretty tricky. I did not go super basic, like break down step by step, because I'm assuming you've got all the introductory videos and tools under your belt. But if you need to review, check out the other videos that are on my Calculus 2 video lectures playlist. All right, happy studying.